G'day chemistry students. In this video we're going to be looking at dot points 5.1.2, 3 and 4. Again, we're going to be looking at different kinds of equilibrium and non-equilibrium systems and be using knowledge and concepts that we've already looked at within the scope of this course to explain how those equilibrium systems come to be. Let's get into it. Now, the first question that I want to be focusing on is how a dynamic equilibrium actually forms. And to explain that, we need to be looking at reaction rate, and in particular, things that will change the rate of reaction. So these are things that we've already looked about when we looked at collision theory in Module 3. We're going to be revisiting those now because by a definition of dynamic equilibrium, we know that the rate of reaction of the forward and the reverse process will be equal. So to better understand how that comes to be, how the reaction rate of two processes equalize, we need to be looking at how reaction rates for different processes can be changed. The first one has to do with energy, the first way to change reaction rate. So if we were to increase reaction rate in ways that involve energy, what we would be doing is ensuring that more particles are actually able to meet those energy requirements, that energy of activation. So for example, by increasing the temperature or introducing a catalyst, that will mean that more of the particles are able to collide with enough energy, which then means that that collision will be successful. In those examples where we change temperature or catalyst, we're not really seeing any increase or decrease in the number of collisions, just the number or a larger portion of successful collisions. What that will mean is that there are more reactions occurring per second and thus a higher reaction rate. But the one that we're going to be focusing on a little bit more to answer our question today is looking at increasing the number of reacting particles. Now, a lot of the time that means that we're looking at changing concentration. That's when we're reacting with gases or substances in solution, which is mostly the kind of reactions that we focus on within the scope of this module, as well as Module 6 as well. So by increasing the number of particles available to react or increasing the concentration, you increase the number of collisions. You're not really changing the energy setup, so the number of successful collisions remains the same, but there are more collisions in total. If there are more collisions, then we would expect there to be more reactions per second, and thus a higher reaction rate. On the flip side to that, if you decrease the number of reacting particles, then you're going to end up having a lower reaction rate because there are less collisions and less reactions happening. So to look at how dynamic equilibrium forms, we're going to be looking at a very common, very basic example of equilibrium. So you can have a container of nitrogen dioxide and dinitrogen tetraoxide, a brown and colorless gas. And when they're in a container, they can react and form equilibrium. So what that means is that you can have two nitrogen dioxides combining together to form dinitrogen tetraoxide, but that dinitrogen tetraoxide can also decompose and form nitrogen dioxide. And both of those things can happen at exactly the same time. Just because you have both of those chemicals in a container, however, does not necessarily mean that it's a dynamic equilibrium. You might have, for example, like we've got down here, an excess of one chemical and not the other. At that stage, the rates of reactions going both ways are not actually the same. You need to let the container or the system actually settle itself out and reach dynamic equilibrium. Those containers just don't automatically have that happen necessarily straight away. So we're going to use this example here. We're going to be looking at thinking about a container that only has dinitrogen tetraoxide in it to begin with. And in particular, we have 1 mole exactly. So what that's going to mean is that the forward reaction from brown to colorless can't actually proceed because there's no nitrogen dioxide. What there is, though, is an excess of dinitrogen tetraoxide. So the reverse process will immediately proceed. And as I said a second ago, the forward process can't actually happen because there's no nitrogen dioxide able to react. So as the dinitrogen tetraoxide reacts, the reaction rate of the reverse process will decrease. So because there's less of those N2O4 particles, that's going to mean that there's going to be a lower reaction rate of that reverse process. Also, the reaction rate for the forward process will begin to increase. As we increase the number of nitrogen dioxide particles, there's more particles that are able to react and reform into that dinitrogen tetraoxide, that N2O4. So what we'll find is that the forward process from left to right will continue to increase as we form more and more and more nitrogen dioxide. And the reverse process, the decomposition of dinitrogen tetraoxide into nitrogen dioxide going from right to left, that reaction rate will continue to decrease as we decrease the number of dinitrogen tetraoxides, the colorless gas. There will be less particles available for that reaction. And that will continue to happen until eventually what we find is that the forward process, its reaction rate has increased and increased and increased to match the reaction rate of the decreasing reverse process. So in other words, when the reverse process has exactly the same reaction rate as the forward process, then what we're going to find is that we enter a state of dynamic equilibrium. If the system is left B, there's nothing else happening in the system, what you're going to find is that there's not going to be an increase or decrease of the reactants or the products in this equilibrium at all. That the number of nitrogen dioxide particles and the number of nitrogen tetraoxide particles will remain the same. And we can start to see this and appreciate this when we begin to graph some of these relationships. So what I sort of explained in words, but now we can start to see in pictures, is that the reaction rate of the reverse process here is at its absolute highest. And the reaction rate of the forward process was exactly 0 at the beginning because there wasn't any particles of nitrogen dioxide to begin with. However, as the reaction proceeds and the number of dinitrogen tetraoxide particles decreases, so too does the rate of the reverse process. And as we increase the number of nitrogen dioxide particles, that forward process, its reaction rate will increase as well until the reaction rates are perfectly equal. And what that means is that equilibrium has been achieved. At this point, you're not going to find that the forward or reverse process is going to dominate the other. We have reached that point of equilibrium unless some other external change happens. Taking this a little bit further, we can also look at what's happening to the number of particles or the concentration. And so what we'll see is that as the rate of reaction for our reverse process decreases, we also see a decrease in the number of dinitrogen tetraoxide particles as well. And over here, the note that I've made, that is because there's a reduction in the number of collisions, going back to our collision theory idea. For the other reaction, the forward process, we see that as we increase our rate of reaction for the forward process, this is because the concentration of our nitrogen dioxide is increasing as well. And so you'll see that the curves have a very similar shape and that they both flatline at the point of equilibrium. All lines are flatlining. But what we can see here is that the rate of reaction is the same and doesn't change. It's a little bit different for concentration though, because the concentrations of the nitrogen oxide and the dinitrogen tetraoxide are different, but they're no longer changing. They flatline in the same way that the reaction rate does. The other thing that we can be looking at as well is why some reactions might not be in dynamic equilibrium. So that would be a static equilibrium or a non-equilibrium system like we looked at last lesson. And that could be because some of our equilibrium conditions for some of the conditions for dynamic equilibrium may not actually be being met. So for example, both processes may not be spontaneous. We might have an open system, or maybe the forward or reverse reaction may not be meeting the activation energy requirements. And so we can be looking at spontaneity by using our delta G equation. We may also know just by doing some qualitative tests that if we have an endothermic process that decreases in entropy, that reaction is probably not going to be spontaneous, and then may explain why it cannot form a dynamic equilibrium. But these are all concepts that we can revisit from Module 4, and we might do a little bit of that in class. Another reason may be that the system may not be closed, which means that there's a transfer of mass, that reactants or products might be moving away, which means that they cannot actually establish an appropriate equilibrium. And we may also find that one of our processes may have too big of an activation energy to be occurring under whatever set conditions we're looking at. Usually we would be looking at under standard conditions, normal atmospheric pressure, 25 degrees Celsius. There's a little bit more nuance to diagnosing why a system may not be in dynamic equilibrium and why it might be static or non. I'm not going to go into too much depth into this video. It's probably been going long enough as it is. But by all means, you can have a look over this Venn diagram to see a little bit more detail as to why a reaction may not be achieving dynamic equilibrium. Thank you very much. In the next video, what we're going to be looking at is Le Chatelier's principle, which is all about equilibrium and how we can change the way that equilibrium works. And we can explain that again using some of our concepts from collision theory. But until then, have a good one.